This video briefly explores the manipulation of airflow known as the Venturi effect, which is seen in aircraft and high-performance race cars. Before analyzing its application, it is important to understand what is the Venturi effect.
The airflow lines being drawn show the airflow through the entry of the Venturi tunnel on the diagram. This middle section is the constriction region, in which airflow must move faster. To observe this, let's first look at the entry of the Venturi tunnel. When we consider the volume of air moving through this section of the tunnel, let's assume that it takes 1 second for airflow to move through this section. There's a law which we will cover later, which says that the volume which moves through this part of the cylinder in 1 second must also move through the smaller section in the middle at the same rate. Hence, as the cross-sectional area of this middle region is lower, and hence the volume of this middle region is lower, the air must move faster to cover the same volume at the same rate. If we were to say that the middle section, for example, is a quarter of the volume of the front section, we would then have to say that airflow moves 4 times as fast, hence it only takes a quarter of a second to move through this middle section. The funnel-like parts of the Venturi tunnel allow the air to slowly change shape. This is all governed by the equation V1 over T1 equals V2 over T2, or also known as V1 T2 equals V2 T1, conserving volumetric flow rate.
I shall now describe the implementation of the Venturi effect in Formula 1 and its specific use in the form of the ground effect. In order to understand this, it is first important to grasp the concept of why this effect was needed in the first place. In the diagram shown below, we can see particles of air flowing over the body of a Formula 1 car. Inherently, the flow of these particles due to the shape of the body cause downforce, which allows the car to stay on the track and stick to the track. As you can see here, the rear wing acts as a method to help propel air upwards to allow for more downforce. However, this not only provides downforce, but it also disrupts the flow of air, and eventually this can lead to what is known as drag. Drag is what will slow down a car on a fast straight, which is not a desired effect. In order to find that sweet point between losing speed on the straights from the drag caused by the rear wing, but still having enough cornering speed, engineers decided using a Venturi tunnel under the car was the best way to go. A Venturi tunnel will now be drawn on this car in the form of a black line. As you will see at the back of the black line, it's sloped upwards to gently allow for the air to return to its free flow velocity. The flow of air under the car at a high pressure is represented by this red arrow. The air flowing under the car via this red arrow will be at a very high pressure due to its constriction in the Venturi tunnel. The difference in pressure, i.e. shown by the blue line, is what causes the suction effect towards the ground. The difference in the two pressures is what causes the suction effect. In order to make sure all the air flows through the Venturi tunnel, a skirt, which is essentially just a piece of bodywork, is added below the car. This makes sure all of the air passes through the tunnel, increasing the effect of Venturi effect and increasing downforce. Next, I will describe the use of the Venturi effect in airplanes, specifically around the wing, and how the Venturi effect is able to cause lift. Here we can see the basic diagram of a wing. The direction of travel is here. This means that air will be flowing at the wing in the opposite direction. The airflow under the wing is uninterrupted, as you can see. This is not the same for the airflow over the wing. The airflow over the wing becomes compressed, and this leads into the use of the Venturi effect. As you can see, there must be a difference in pressure between these two layers of air, above the wing and below it. Above the wing, where the air is compressed, there will obviously be greater volume of air. And we know from what I earlier stated is that when the volume is higher, the pressure therefore must be lower. As you can see below the wing, the volume of air is lower, and therefore inversely the pressure must be higher. This creates a difference in pressure. A difference in pressure, as we've seen before, is what causes lift or downforce respectively.